to you about how drones can help with flood hazard modeling. So how drones can help with flood hazard modeling. In particular, I'll be talking about something called street level flood hazard modeling. So as the name suggests, this is not a regional or global scale flood hazard modeling, but it's flood hazard modeling that where we predict the parameters and the dynamics of flooding at the scales important at the individual streets or around properties. So these are very detailed models, very fine resolution flood hazard models that we built. They're the most accurate, the most detailed, and stakeholders and decision makers, emergency response people, as well as citizens who live in flood hazard areas can use. And in terms of flood hazard modeling, this data entails, first of all, some idea of the surface that we modeling flow on. So we usually use LiDAR, digital terrain models. We also need some idea of the type of land cover in our site that we're modeling. So, is it a concrete surface? Is it a grassy surface? Is it bare soil? Because each one of these different surface types can affect the velocities of flows. We also need infrastructure information. Are there any buildings? Are there any flood walls? And then finally, we also need validation data. So in order to figure out how good a model predicts a certain flood event, we can only really figure out how well it does by comparing the predictions of our models to actual observations of the flood we're trying to simulate. So this data is not always available. It's very time-consuming to collect a lot of this data. It's very expensive. LiDAR surveys can cost from several $100,000s to millions of dollars, depending on the scale of the mapping. And also, if conditions in our site change, if a river, a stream gets rerouted, if a new underpass is built, if a new housing community is built, we may need to resurvey some of these areas, and so that adds to the cost. And so what that means is that only really wealthy nations, wealthy cities have been able to acquire the kind of data we need for street-level flood hazard modeling. And a lot of developing countries don't have the abilities to do this kind of modeling, and those are usually the cities in developing countries that suffer the biggest losses from flooding. All right, so how can drones help? Well, we've seen that drones can acquire very detailed photographs that can be flown using photogrammetric principles, and we can extract all kinds of useful data. And in terms of flood hazard mapping, we've seen this morning that we can obtain very detailed 3D terrain models, right, which will be a surface over which we do flood hazard modeling on. The images that we capture can be processed to figure out what land cover types we have in our site. We can also detect if there are buildings. We can detect if there are walls that may reroute the flows in certain areas. And also, if we fly drones during flood events, we can actually capture imagery of flood extents that we can use to validate our models with. Drones are really cheap. They're very easy to fly. They're fast to deploy. So in theory, drones could be a great resource to collect data needed for flood hazard modeling, street-level flood hazard modeling. In practice, we're trying to test it out, and we have a couple sites that we're working on right now. The main one that I have data for is a site in La Paz, Mexico. It's on the Sea of Cortez, not on the Pacific Ocean, but on the Sea of Cortez. The city is surrounded by mountains and hills. So these are the mountains over here. The city's on the Sea of Cortez here. You can see this is actually a photo that I took from a drone, and you can see the mountains in the background here. It's a very rapidly expanding city. Population is currently about 250,000, but it's growing at about a 5% rate every year. It's rapidly expanding in terms of population, but also infrastructure. In terms of climate, it's very dry, kind of like here, but in the summer and fall months, they get very intense rainfall events. So flooding is a big issue. And usually what happens is that rain falls onto these mountains, and then it runs off the side of the mountains and channels into these really long avenues that pretty much connect the mountains to the Sea of Cortez. And so during these rainfall events, you see really rapid flows coming down some of the streets, and they tear up the concrete, they destroy buildings, they really impact business in the city. And if you look at the dates on some of these videos here, August 2012, August 2014, October 2015, so almost every year they see some level of flooding. Now the issue is that La Paz currently doesn't have fine resolution data for flood hazard modeling. And so they don't have a detailed flood hazard mapping program. And so a lot of the infrastructure is being built, a lot of these housing communities are being built in areas that potentially have very high flood hazard. And so when people end up buying some of these properties, they might not be aware of what the flood hazard is. And in a couple of years, they might lose their property. And so a lot of there are civil societies in the city that are taking matters. Like the government doesn't seem to help much in La Paz. And so civil society groups are taking matters in their own hands and is going out building green infrastructure, rain tanks, infiltration gardens to try to reduce some of the runoff that ends up tearing up some of these streets. And we'd like to help them. We'd like to build a very detailed flood hazard model of the city, of the whole watershed, and tell them where they can more accurately place some of this green infrastructure to mitigate their hazard, reduce the losses. So we took a drone down to La Paz, little Phantom 4, weighs 3 pounds. It's very easy to travel with this little thing. Has a 12 megapixel camera installed in it. It has GPS built in. 20-minute flying time, and the cost is minimal. I bought this unit about a year and a half ago. It cost me $1,800, including extra batteries. Nowadays, you can buy one for $900, a refurbished unit with a couple of extra batteries. So the cost of these things really has come down, and it's great because we want these communities to be able to do their own mapping of terrain topographies, of land cover types, and so telling them that some of these units are so cheap to buy and use, is a great resource for them. And instead of telling them they need to buy a really expensive LiDAR system, for example. All right, so I flew this Phantom 4 in a rural canyon community initially. So this was my first attempt in flying this drone. And I flew it autonomously using drone deploy at about 300 to 400 feet elevation. Altitude above ground. The area I flew is about half a square kilometer, so about 100 acres. It took less than 10 minutes to fly, collected 222 images. These images have a pretty big overlap. It doesn't show on that figure up there, but about 70% overlap between images. And then I used photoscan to process these images photogrammetrically and obtained a digital terrain model that looks like this. So we can see the canyons in this canyon area here. And we can actually drape the area photos that we captured onto this terrain data so we get this 3D view of what the canyons look like. To compare some of this drone-derived data to currently available data for flood hazard modeling in the site, I put this little figure together. So the top panel is currently available data, for example. So in the top left-hand corner, we have 1 meter Iconos satellite imagery. So this is to do visual observations of our site. Down at the bottom here, and so the resolution is a meter. Down here we have 4 centimeter resolution ortho photograph from our drone derived data. So really fine resolution data that we can obtain flying at about 300 to 400 feet height. Top right hand corner is topographic data that's currently available for the site. This is NASA's shuttle radar topography mission data. So it's 30-meter resolution. That's 100 feet. So what that means is that for every 100 feet, we only have one value of elevation. So it's very coarse data. If you look at an image, you can't really see any landforms. You don't know what's going on, really. You can look at the elevations, but it doesn't give you a clear picture of what kind of landforms are in this site. And then down here, we have our drone-derived terrain model at 15 centimeter resolution. And now you can clearly see these canyons. You can see where water would accumulate during rainfall events. If we zoom in a little bit onto the site, the Iconos imagery in ArcGIS, if we zoomed in too far onto a specific site, the data actually starts to get blurred. So that's a 24 by 43 meter area. So we should be able to see pixels, but it gets blurred, so we can't really derive any information by looking at that imagery. Our drone picture, on the other hand, we can see individual rocks, we can see shrubs. Really great data if we were to use this for vegetation mapping, for example. And then top right-hand corner again is our shuttle radar topography mission data, 30-meter resolution. Again, very coarse, you can't really see any landforms. Again, a drone data is very fine resolution. We can see where buildings are. We can actually detect a little dam wall that is only about 1/2 meter wide by a couple meters tall. So we can really detect small-scale features that can have a big impact on the flow of flooding. All right, so, and then here we flew over the city of La Paz, so you can see some infrastructure, urban infrastructure buildings. You can see walls around properties as well. We can create beautiful images, 3D images of buildings. But I want to show you what it looks like if we use some of this data for actual flood hazard mapping. So I'm going to fly into this site down here called El Ciruelito. That's an urban canyon I showed you earlier the data for. So here's our satellite imagery of the site. Here's our shuttle radar topography mission data, 30-meter resolution, very coarse. And so if we simulate rainfall falling onto this area here, the rainfall will move from high ground towards low ground. And because the data is so coarse, you see that it all ends up accumulating in this one little spot here, which is a local depression. So all of this flow ends up, getting to this point. And it doesn't look very physical, right? It doesn't look physically meaningful because the data is so coarse. Now, if we take our drone-derived topography data, you can see all the canyons there. We simulate rainfall falling onto the side. Now you can see that the rainfall is moving off the sides of these canyons into these depressions, and then we'll start moving downstream. Okay, so it looks physically a lot more realistic than using shuttle radar topography mission data. And we can see where water might accumulate because there might be some blockage or some feature retaining water there. In this case, it's little dam walls that are trying to capture the flow and let it infiltrate into the ground. Okay, now I'm flying into this Manglito site. So that's our urban test site. So here's our satellite imagery of the site. Again, here's our shuttle radar topography mission data, very coarse. Again, we do flood modeling, so we simulate rainfall onto the side. We see that water is now accumulating at 3 different depressions. Again, it doesn't look realistically very meaningful. Now we have a drone-derived data, so you can see where the streets are, you can see where the buildings are. Again, if we do rainfall modeling on here, you can see that the water is accumulating now along streets and depressions in the ground. A lot more realistic. But not all is well in the world of data that we can derive from drone photography. So here I flew onto a different site called the Agua Escondida site. It's along a major river in La Paz, and so you can see the detail in the terrain model that we can extract from drone photogrammetry. In some cases, you can even see tire marks in the sand. It's really impressive. But if we look at the actual slopes in this terrain data set, so I created some profiles here. So flow is actually supposed to go from the top right-hand corner to the bottom left-hand corner, right? So the river flows this way. But if I draw a profile from the downstream end towards the upstream end, I'm actually seeing this happening. So the stream is sloped the wrong way. Flows will be going the wrong way. And also, if I draw a profile across the stream, so this is towards the mountains, from the mountains towards the Sea of Cortez, we have the correct type of slope, but it's actually much steeper than reality. So this happens because I flew my drone using a built-in GPS, which is pretty inaccurate, 1 to 5 meter resolution, and I didn't do any processing of the air photography with ground control points. So this was just using the built-in the GPS data from the built-in GPS. So if I were to use this data for flood hazard mapping, my water would be going all over the place. So I have to be really careful how to process the data to get good data. But the initial results are encouraging. So drone photogrammetry is capable to collect very fine resolution data. If it's processed correctly, we can actually get the right slopes in for flood hazard mapping. It can be flown very easily. Most people will actually find it fun to set up and fly these things. And the results from using this data for flood hazard mapping is a lot better than if we use very coarse resolution data that's currently available in some of these sites. The challenge, though, is right now my test sites were about 100 acres in size, half a square kilometer. The challenge is we cannot use these small data sets for actual flood hazard mapping across a whole city. So the challenge is to scale up. We have to be able to map out a whole city or a whole watershed. And so we want to involve the community to do this. We want to implement citizen science type approaches, a community participation approach, where we make drones available to communities, and we currently have a test site in Malawi in Africa right now to try this out. We make some of these drones available to community members, volunteers. We train them on how to use these drones. They themselves go out and train others. And so before we know, we have a dedicated group of volunteers that over time will go out and map different parts of the watershed. Eventually, we also would like them to help out with processing some of this imagery so that we don't have to do it all ourselves. And so the community itself, the community that's a danger of flooding, is going to be actively involved in capturing the data that will be used for their own flood hazard mapping. We currently are trying this out in Malawi, in the Chilwa Basin. We're currently trying these techniques out in La Paz. But we've also had interest from other cities in Paraguay, Colombia, Nepal. And so we're now trying to get enough funds together to put together several fleets of drones that we can deploy to these communities. And hopefully over time implement these street-level flood hazard mapping approaches even for these communities. All right, thanks very much. That's all I have.
Questions?
Yeah.
What have you found flight restrictions in other countries?
Yeah, so that's part of the reason why we went down to Mexico. It's a lot less controlled in Mexico than it is in here. I think Mexico is supposed to be one of the most liberal countries when it comes to drone regulations. They have rules, of course, but they don't have so many no-fly zones. So obviously you have to stay away from airports. They actually don't say don't fly over buildings. They say you're allowed to fly over buildings as long as you fly 50 meters above a building, so you can't get too close to buildings. So yeah, Mexico was a lot easier to fly than Orange County, for example, where I'm based. But as far as I know, Malawi doesn't even have any regulations. You know, we're flying over little villages. Most of it is rural anyway. You know, so there's no big cities that we are mapping over there. So it's easier. In some, not everywhere, of course. Like Australia has very strict flying regulations, just like here. But some of the developing countries that we're looking at, they're not quite as far advanced with implementing regulations.
Do you find it's easier on the ground control sort of elevation corrections, 10, 15 points, or is there any?
Yeah, so
you use the old shuttle radar topography to help that?
Yeah, no, I had a local surveyor go out, and I used 5 points for a half a square kilometer area, and that was great. I got accuracies of about 30 centimeters vertical, but I think in terms of ground control points, I don't think I will need that many. I'm not looking at getting a couple of centimeter accuracies. 20, 30 centimeters accuracies are usually fine, similar to LiDAR data, are fine for street level flood hazard modeling. So yeah, I think I'm going to have to do a little more testing on see how many ground control points I can get away with to get reasonable accuracies. But also I'd like to test out flying drones that have better GPS on board, so I could potentially avoid doing the ground control side of things, just because it's a lot easier than having to send people out remote parts of the watershed and do the ground control point collection. So yeah, these are all things that we're testing right now.